Hi everyone, a very warm welcome to you all to the chemistry session. So I hope everybody is doing great. And we had started off with nucleophilic substitution in the last session, and that too is a very important topic. So nucleophilic substitution, when the nucleophile replaces the halide ion in the alkyl halide and the halide ion gets removed in the form of a leaving group, right? So that is what a nucleophilic substitution is. Now what we had started off with was the type of nucleophilic substitution. First was the Sn1 and the second one was Sn2. This is none other than substitution, nucleophilic, nucleophilic, unimolecular, right? And that is substitution, nucleophilic, bimolecular. Everybody remembers that or not? Nucleophilic, bimolecular, right? Why this is known as unimolecular and why this is known as bimolecular? Uni because it stands for 1, that is the order for the rate equation is 1. Here the order for the rate equation is 2. So the rate depends upon the concentration of the alkyl halide, right? And here the rate depends upon the concentration of the alkyl halide along with the nucleophile which is taken. Fine. So the order over here is 2 and the order over here is just 1. Fine. So that is how we consider the substitution nucleophilic reactions, right? Either you can write it as a nucleophilic substitution or substitution nucleophilic. It's either of the ways is correct. Now what we were on to was the Sn1. Let me just quickly brief you the mechanism. So here it is, Sn1. So it's a two-step reaction as I told you, and the main thing is the formation of carbocation over here. Step 1. I'm writing the general reaction for it now. I have taken up the nucleophile in the presence of polar protic solvent. So have you given a thought about it, what polar protic actually is? If not, I'll tell you. Polar protic solvent I have taken. First step is formation of carbocation. So that is the carbocation that I have formed. Clear? That was the first step, and indeed this is nothing but the slow step with which I consider my rate equation, the rate determining step. Fine. Step 2. The carbocation then reacts with the nucleophile and we get our desired product. Fine. So this particular step, the last step is the first one. Clear? Now I had asked you a question that why only the rate equation is dependent upon the slow step and why not the fast? The fast step is so much fast that we cannot find out the concentrations of all of these species which is involved. It is very difficult to observe such a fast step in comparison with the slow step. In slow step, I can very well recognize, I can very well find out the amounts of each and every species which is involved, and that is how we can define a rate for that, right? So that is why every time the slow step is the rate determining step. So these are the two steps involved. What is the specifications for Sn1 now? R positive, the carbocation, right? The geometry, trigonal planar. Fine. So it is somewhat like this. Let me just make that again. Maybe something like this, right? It depends upon the type of carbocation which is formed. So I'm randomly taking the secondary carbocation over here. trigonal planar geometry. You need to remember that attack could be possible from this side or that side. That is the final attack of the nucleophile I am talking about. So either of the ways I can get the product. Now, what all is dependent? What all are the factors which is dependent upon the Sn1? The factors which actually speeds up the reaction, the factor which actually lets the reaction not to happen. What are the factors for Sn1? So this particular topic, an important one, right? Factors affecting Sn1 reaction. Now, what all are the factors? So since you can see over here, there is the formation of carbocation. That means what? The main thing is this only. The carbocation must be very stable, which is formed, and that is how it will decide the rate of the Sn1. Stable the carbocation formed, faster will be the reaction, right? So first and foremost is the type of carbocation. Let us just see. So first is type of carbocation, right? So the type of carbocation, stable the carbocation, which is the most stable carbocation that we can form? It's none other than the tertiary carbocation followed by secondary, primary and 0 degree, right? So it is stable the carbocation formed, faster is the Sn1 reaction, right? So thereby, what is the stability order for the carbocation if I consider? It's tertiary, secondary, primary and then finally the 0 degree one. May not, again I'm telling you, may not find this 0 degree term in the book, but what does that 0 degree signifies? It signifies methyl carbocation. Clear? I need to make the secondary one now, so it will be, right or not, the secondary one and the tertiary one. So this is the tertiary one. Clear? So which is the most stable and why these are stable? Everybody knows it or not? The reason behind this, these alkyl groups are donating, thereby stabilizing the positive charge. That is what the reason is. I am not going into the deep discussion of it. Now, as soon as a stable carbocation is formed, I can have the nucleophilic attack more faster to it and I can get my desired product very quickly. Clear? So this particular, the tertiary carbocation will be most reactive towards Sn1. Fine. Now, the use of nucleophile. What type of a nucleophile we need to use, right? That is another factor. So let us just consider factor number 2. Type of nucleophile. Now, if you consider the rate equation for Sn1, what is the rate equation? What does it say? The rate basically, what is the rate? I am measuring the speed by the rate by which the reaction is happening. The rate by which the reaction is happening, the speed by which the reaction is happening, right? So that is what the rate defines. Now the rate is dependent upon Rx. What is this Rx over here? Rx is none other than the concentration of the alkyl halide, the main reactant, the main substrate that is taken. So it does not depend upon anywhere on the nucleophilic concentration, right? As the rate equation says it all. So there is no mentioning of the nucleophile. That means the rate, the speed of the reaction does not depend upon the nucleophilic concentration. So I can take either strong or I can take either a poor nucleophile. Over here, what will I be taking is, it's really specific, we will be taking poor nucleophile, right? Why is that so? If I take up a very strong nucleophile, what will it do? It can try to interact with alkyl halide in a very fast manner that it does not give time for the formation of carbocation. All these things which I am explaining over here is just for your information, right? Just for your basic understanding, to develop an understanding for this particular mechanism, why each and everything is happening, right? So over here, type of nucleophile must be poor. The rate does not depend on the concentration of nucleophile, right? So that is why I am taking the poor nucleophile. If I take up the strong, what will happen? In case of strong, the reaction could happen in just one step, right? So strong nucleophile may lead to one step process, right? One step process. And do you know what this one step process known as? It's none other than the Sn2 mechanism. Yes, we'll be discussing this particular mechanism as well. So it gets included under the category of Sn2 basically. So that is how we consider the poor nucleophile over here. That means not a very good nucleophile we are using. Right? Now comes up something which is very, very important, that is the leaving group. Can you see the leaving group over here? X negative will be written over here, or I can write it in the first step itself. So this is none other than the leaving group, right? This particular leaving group must be very good. So that is the another factor, the type of leaving group that we are going to consider. So I hope everybody has written this. I'll be rubbing this off. So it's the the third one, the third factor, type of leaving group. And something about the leaving group, I feel that I have explained this particular thing about the leaving group in the 11th standard, and that too in the organic chemistry. You need to refer those sessions as well. Otherwise, I'm explaining you and giving you a general idea of it, right? So the general idea, what is a leaving group basically? Which leaves the vicinity, which leaves the substrate, that is what the leaving group is. Which leaves the substrate. The type of leaving group means it could be good or bad, right? So the two types could be good and bad. How can we judge that? A good leaving group basically is which is having enough space within it, right? Can you observe something over here? This X and X, when it tried to leave from the main substrate, it took all the electrons to it, right? It took all the negative charge and then was removed. Fine. That means it is having enough capability to hold on those electrons. How does it have so much of enough capability? That means it is having enough space. It is bigger in size. Clear? So that is what a good leaving group is. Good leaving group which has enough accommodation space to hold the, or to be very specific, I am using the technical word over here, to hold or disperse the negative charge inside it, right? So how can it have the enough accommodation? Via having the bigger space, bigger size. So if I consider different halogens, out of all the halogens, out of all the halides, which is the better leaving group? The one having biggest size. That is, if I go down the group, fluorine, chlorine, bromine, iodine, so iodine has the biggest size, thereby it will be serving as the better leaving group, or you can say the best out of 4. Fine? So out of halides, which is the best? Fluorine is the least, then chlorine, then bromine, and then iodine. So iodine is the best leaving group of all, out of all, since this is having the biggest size, right? So it is having the biggest size. Fine. So that is what the reason behind a better leaving group is. Clear? So the leaving group, if this is I negative, it is very well and it will quickly leave the substrate. A good leaving group, I am writing this down here. Good leaving group will leave the substrate quickly. Fine. So that was it under the category of leaving group. That was the factor number 3. Let's move on to the very next factor. Next factor is, I am just giving you an idea about this factor, is polar protic solvent. Now first of all, the point is what polar protic solvent is, right? So let me just again rub this off, or let me just rub this particular portion because we are almost done with Sn1, right? Now, fourth factor, the solvent, the choice of solvent. So first of all, I am taking polar protic, I say. What is the meaning of polar protic? The meaning of polar protic is it must have the polarity, right? And it must have proton donating capability. So first thing is polarity it must possess, and second thing, proton donation capability. Fine. So it is ready to give H positive and it's polar as well. What kind of solvents I can use over here? So the solvents that can be used over here are water, right? It is polar and it can donate H plus ions. Alcohol, C2H5OH, fine. This is also a solvent that can be used. Again, it can donate the H positive, right? And also it has got the polarity as well. Or what we can use is acetic acid we can use, fine. So generally water is what we use over here, fine. And that is just a simple idea about it. No need to go into the detail because it's not included in your syllabus basically. Why I am telling you this is the application of it might come in some of the questions, right? But that too the chances are very less. So basically why we are using this? Why? Because it helps in cleavage of Rx bond. Why this helps in the cleavage of Rx bond? Because since this is polar, it will be having positive and negative poles, which will try to attract R and X, right? This is also having poles in it, and due to such polar interactions, there will be more likely, this bond is more likely to get cleaved. Fine. So that is why we are using polar protic. I hope that is completely clear to you. And that was it under the category of Sn1. So I hope everybody has got it. That was quite a good process actually. I really like this process because it has got so many kinds of explanations, and we get to know about each and every type of compound which is involved in it and the role of that, right? So that was very, very important. Even all the factors that I have discussed till now holds importance as per your examination, especially this leaving group part and the carbocation. Clear? Now let's take up the very next, that is known as the Sn2 mechanism. So as I told you, Sn2 mechanism, substitution nucleophilic bimolecular, right? So I had given you a hint regarding this, that Sn2 mechanism is basically known as, now hear me out very clearly, concerted mechanism, right? Now what is this term? It's not concentrated but concerted. Concerted mechanism or concerted reaction is the one which happens in just one step, right? So this particular reaction, it happens in one step, right? It's a one-step process basically. Fine. So that is why it is known as the concerted mechanism. What is the main thing which is formed over here, which we are concerned of, is the transition state. Is formed. Fine. So here the transition state is formed, and now let's move on to the very next reaction. The very simple procedure that I am going to tell you over here. Rx, alkyl halide, and the nucleophile in the presence of some solvent. Now what kind of a solvent do we take over here is polar aprotic solvent, right? Aprotic solvent. Again, now you can judge very well. Why polar? Because it is having polarities. Why aprotic? Now I don't want any liberation of H plus ions, right? So that is why I am taking the one which is aprotic, which do not donate H positive ions. Fine. What do we get? So that is one step process, only and only one step process. And what will be happening is, the main thing is the formation of the transition state. Let us just see how the transition state is getting formed. So the nucleophile actually attacks from the back side, right? It is a backside attack basically. Right? So it attacks from the back side, it does not come from the front, because it will face so many repulsions due to this electronegative atom, right? So instead of preferring from the front, it goes from the back and then tries to attack, right? So it goes from the back and attacks, it forms a transition state. What is that transition state? The nucleophile tries to get attached with the R, whereas this X tries to leave the vicinity just in order to reduce the number of repulsions, right? Reduce the steric hindrances basically. So now you can see this bond is smaller because they are now getting attached with each other, whereas this particular bond is kind of very long, it's stretched, thereby indicating that this is about to just break, right? So this bond is about to break, and this is about to get formed. Fine. So that is how the transition state is. This is known as the transition state. Let me just write it over here. Fine. So once we are done with the transition state, what do we obtain over here? We obtain is this bond breaks out and we get NuR, right? So instead of getting RNu, what I am getting is, I am getting NuR. That means now the nucleophile has been attached from the back side. Thereby, what do we get is, we got an inverted product. You can see, I am not getting a simple, the usual product that I was getting in the Sn1, but the inverted one, right? So this is the inverted product that we have got. That means this particular process is known as nothing but Walden inversion, right? So this is Walden inversion, accompanied by the inversion of configuration, right? So this inverted product is having inverted configuration also. Now what is this inverted configuration? We will be discussing this aspect in the next session, right? And till then what you need to do is revise this entire process, because I will be dealing with slight stoichiometry, right? Not the stoichiometry, sorry, the stereochemistry part of this particular reaction. I will be discussing this reaction in 3D aspect, right? So we will get to know very easily what all is happening in it, right? Have a very good day.